Hello and welcome back. In this video, the first example I want to do is to look at a case when the definite integral does not correspond to area. So let me draw a picture of what this is going to look like, and then we'll take the integral and we'll see what happens. So I'm taking the integral of x, as in the line y is equal to x, and I'm going from -1 to +1. So when we look at the area between the curve and the x-axis, we've got these two triangles. They should be the same size, but one is up here on top of the x-axis, and one is over here below the x-axis. So the question is what's going to happen, and I'll give you a hint. It's maybe not going to correspond to area. So when I take the indefinite integral, the antiderivative of x, I'm going to raise x to the one higher power, and I'm going to divide by that power. So this is just taking the antiderivative, and then we plug in our bounds, 1 and -1. So we get 1/2 x squared, so x is going to be 1 squared, and I'm going to subtract 1/2 times -1 squared. Well, 1 squared is just 1, times 1/2 is 1/2. -1 squared is also 1, because the negative signs cancel out, and 1 times 1/2 is 1/2, and what we get is 0. But there's clearly an area here. So what is happening? And the answer is, well, the area up here to the integral is going to count as positive area, and the area down here is going to count as negative area. Now, there really is no such thing as positive area and negative area. If you have a shape and you look at the area of that shape, it's never negative. There's no such thing as negative area. So what I'm saying here is maybe a little bit inaccurate, but what happens here is that we're just going to add up all of the area on top. We're going to add up all of the area on the bottom, and we're going to subtract those two numbers. So we're just counting all of the area on top as positive numbers, and all of the area on bottom as negative numbers. And as it just so happens, in this case, if we're going from -1 to 1, we have the same area on top and the same area on bottom, so they cancel out exactly. So area for an integral, if I could spell, for an integral is signed. So we consider the area above the x-axis to be positive, the area below the x-axis to be negative, meaning if we take an integral, we're going to take all the area above the x-axis and we're going to subtract all the area below the x-axis, and that will be our answer. So again, here we've got another integral, and we're taking I can't do that quite. So let's do this instead. This will be a little bit better. So we'll take the integral from -2 to 1 of x to the 1/3 minus x to the 1/5. This is a function that I don't think I could draw very well by hand. I know what x to the 1/3 roughly looks like and what x to the 1/5 roughly looks like, but at the same time, it's going to be fairly hard to draw by hand. So rather than trying to calculate an area by looking at it, let's just take this integral. So if I want to take the integral of x raised to a power, I take x and I raise it to the one higher power, and I divide by that power. So I'm going to divide by 4/3, which is the same thing as multiplying by 3/4. And then I'm going to, so I have a minus sign here, so I'm going to subtract. So x to the 1/5 power, that will become x to the 6/5 power, but I need to divide by 6/5, which is the same thing as multiplying by 5/6. And then I plug in my -2 and my 1, and I subtract them. So if I plug in the 1, I'm going to get 3/4 times 1 to the 4/3 minus 5/6 times 1 to the 6/5. I've plugged all that in, and now I'm going to subtract what I get when I plug in -2. So it would be -2 to the 4/3 power minus 5/6 to the, 5/6 times 2 to the 6/5 power. This might be able to simplify a little bit, but -2 to the 4/3 power and -2 to the 6/5 power, I'm not going to be able to simplify all that much. So on this side, I get 3/4 minus 5/6. If I distribute this negative sign, I'm going to get minus 3/4 times -2 to the 4/3 power, minus minus, so that's plus 5/6 times -2 to the 6/5. And again, this would be something that you could easily plug into a calculator if we wanted a decimal version of this. If we want this to be exact and just in integer form, this is almost as good as we're going to get. So yeah, I'll just leave that there. But notice that some of these integrals will have somewhat complicated forms, but ultimately, if we could draw a picture, we would know what this would represent. This would represent the area between the curve and the x-axis, adding the area above and subtracting the area below the x-axis. One thing that's important to mention about when we think about area, or when we think about integrals in particular, we can think about their units. So for instance, when I have v of t being velocity, we would normally think about this, for instance, maybe we're going to measure that in meters per second. This is quite a common unit to measure velocity in. And if we take the derivative of velocity, so if we're taking the derivative of velocity is going to be acceleration. And acceleration is going to be measured in meters per second squared. And again, taking the derivative, we're looking at the change, the rate of change in a value. So if your velocity is changing, that means that you're accelerating. So if your velocity is changing, how fast is it changing? Well, it'll be changing in meters per second. So we end up getting meters per second squared. Now, what happens if we're going backwards? If we take the antiderivative, or the integral, if I could spell today. Well, we're going to be calculating an area, right? So when we think about area, what is the area of this? What are the units going to be measured in? Well, if we're taking meters per second, is going to be the height. So for instance, if this is a triangle, this is going to be 1/2 the height of the triangle, which is going to be in meters per second, and the times the base of the triangle, which is going to be measured in seconds. The 1/2 doesn't have units, so this is just going to be in meters, right? Seconds will cancel out. So the antiderivative, again, this makes sense that it would be measured in meters, because the antiderivative here should be position, which I think is quite often s of t. So the position is going to be measured in meters of something. And in particular, if I take the derivative of position, I get velocity. So when we take an antiderivative, we're actually going to be multiplying by the units on the axis. When we take the derivative, we're going to be dividing. So the derivative of position is velocity. We're going from meters to meters per second. Derivative of velocity is acceleration, which is going to be meters per second squared. When we take antiderivatives and we're moving backwards, we end up multiplying by units of time. So we're going from meters per second squared to meters per second to meters. If we want to take the antiderivative of position, I'm not sure what that would be, but that would be measured in meters times seconds. So maybe that would be something like, yeah, I'm not exactly sure what would be measured in meters times seconds. So units are important. So let's do an example of a question using that involves some units. So the marginal cost of installing a water pipe is going to be given by this formula. Marginal cost is how much is going to be the cost of installation, so per unit. So in this case, the marginal cost of installing a water pipe, I've just come up with this formula. I have no idea if it's accurate, but it's going to be measured in dollars per foot. So so this is, if we want to lay so much pipe, we're going to calculate it using this. But we want to find the cost of laying exactly 100 feet of pipe. So what that means is we're going to have to take an integral, because we have dollars per foot and we want to multiply by feet. Okay, so if this was part one, how much water pipe are we going to be laying? Well, we're going to be laying 100 feet of it, but we're going to start with 0 feet and we're going to go up to 100 feet. So when we want to turn marginal cost into cost, we're going to take an integral. So here we've got 3x to the 1/4 plus 10. And can't forget our dx at the end. So here, again, this is going to be measured in dollars per foot. So we want to essentially multiply by feet, which is going to indicate that we want to take an integral. And this is, again, a fairly straightforward integral to take. We just are going to take the integral of both parts individually. So again, when we are integrating, taking the antiderivative of a sum of functions, we can just take the antiderivative of both individually. The 3 pops out, and then the antiderivative of x to the 1/4 is going to be x to the 5/4 divided by 5/4. And if we're dividing something by 5/4, we're multiplying it by 4/5. And then secondly, we're going to add the antiderivative of 10, which I can think of this as 10 times x to the 0 power. So it's going to become x to the 1st power divided by 1. Cool. So we've taken the antiderivative of both of these, and we're going to plug in our bounds. So here we'll end up getting, so let me simplify this a little bit. 3 times 4/5 is going to be 12/5 times x to the 5/4, so that's going to be 100 to the 5/4 plus 10 times 100. And we're going to subtract when we plug in 0. So it'll be 12/5 times 0 to the 5/4 power plus 10 times 0. Oops. Well, 0 times anything is 0, so that guy we get to ignore. 10 times 0 is 0, so we get to ignore that guy. And we're just left with what's out front. So it's going to be 12/5 times 10 to the 5/4, 100 to the 5/4 power plus 10 times 100 is 1,000. And this is something that we could plug into a calculator really quick in order to solve. And I will consider the next part of this problem in the next video when we look at laying 10 feet more of pipe if we've already laid 100.